Hello, everybody. Um, Today it's my pleasure to introduce Dr. Bertrand Jodoin, who is a professor of mechanical engineering at the University of Ottawa for the past 25 years. He's been actively involved in developing and teaching courses like thermal fluids, thermodynamics, heat transfer, gas dynamics. His research interests include thermal sprays with both experimental and modeling work. And he is a pioneer in the field of gas dynamic spray processes. His contributions to the understanding of the process fundamentals, as well as the development of tailored applications for the aerospace, automotive, and energy sectors, have been acknowledged by many rewards. I'll just go through a few of them. For example, the Journal of Thermal Spray Technology. He got the best paper of the year there. International Spray Conference got the best paper. Springer's Nature Editor Special Selection, which is quite impressive. He got that for the paper on Change the World, one paper at a time. Also, he has an award for exceptional leadership from MITAX and Water Jet Technology Association, Industrial and Municipal Cleaning Association Conference Best Paper Award. Dr. Jodoin has also been recently listed on Stanford's list of the top 2 most cited scientists in the thermal spray field, and he is the inventor of 5 patents, and these have been part of commercial and industrial partnerships, and one of these patents was used on Boeing aircraft in order to repair some of their aircraft skins. So it's my pleasure again to introduce Dr. Jodoin, and I'll leave the floor to him.
Thank you, Dr. or Professor Choueiri. One of the achievements that you didn't mention was my little contribution in getting George Choueiri becoming Dr. Choueiri and then Professor Choueiri. So I take great pride into this, but we won't go further into details about that. So I'll start my presentation. So I'll share my screen here with the this one here, and then I think I can start. Yes, so thank you very much for the invitation. It's a pleasure to talk to your department and so many people. So my presentation is on cold gas dynamic spraying, which is a process I've been working on for many years. As you're going to see, it's actually a fairly deceptively simple process, just like a rocket engine. It's not that complex. But it did change a lot in the coating and additive manufacturing field. And despite being deceptively simple, it has kept me busy for over 25 years. And I think it's going to keep me busy for many, many more years. So I want to share a little bit about that with you all. So to start, I'm going to first show a little movie clip here, and I have the sound there. I hope it's not too loud and that you can hear the sound. But I just have a short clip to get this started, just to get everybody's attention. So I'll start it, and I hope that the sound is on and that everyone can see and hear.
This is the Earth at a time when the dinosaurs roamed a lush and fertile planet. A piece of rock just 6 miles wide. It hit with the force of 10,000 nuclear weapons. 1 trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating blanket of dust the sun was powerless to penetrate for 1,000 years. It happened before. It will happen again. It's just...
Okay, so this is basically the trailer of a movie that was launched the year I started as a professor at the University of Ottawa. The movie was called Armageddon. So most of you were probably not born at this time, or you were very young. And the idea of that movie was that to prevent an asteroid from hitting the surface of the Earth, they were launching a spacecraft, basically a space shuttle, to send people on the asteroid and basically make it explode before it hits the Earth. So that's kind of weird and very Hollywood type of movie. However, it's not that crazy because next week NASA is going to launch with the Johns Hopkins Applied Physics Lab a spacecraft that will actually go try to impact on an asteroid to double check or to verify if we can deviate the trajectory of an asteroid from its path in case this definitely happens on Earth. So the idea is to test if this spacecraft can be launched directed towards this small asteroid and see if we can alter its movement. And it's called the double asteroid redirection test. So you have a very large asteroid here, and it has a moon, which is also an asteroid. It has a smaller moon, which is the typical size of asteroids that hits the Earth or are passing by close to the Earth. And they're going to launch this spacecraft and try to impact it and try to see if we can alter its orbit. So that would be the beginning of a new field of research on kinetic impactor technique to see if we can prevent this if in a few hundred years we get an asteroid that comes close or too close to the Earth. Why we want to do that? Well, you've seen, right? We got the dinosaurs that died because of an asteroid that did impact on the surface of the Earth. And we know that if we do have asteroids that impact on planets like Jupiter's surface here, you see lots of craters, and even on the moon, you get craters there due to asteroids. So that's why we want to prevent that. Now, someone might ask, where is this going? What's the relation with what you were supposed to talk about? Well, actually, when the cold gas dynamics pre-process doesn't work well, we basically reproduce these types of surfaces. So you can see here on the top, this is a substrate that we wanted to coat to build material on top of it that failed miserably, and then we have those craters a bit similar to Jupiter's crater. And here you have a zoom of one of those craters, which is fairly similar to what you have on the moon. So what we're doing in the lab is a bit related to these impacts. However, we don't want them to fail because the objective is to build things, not to destroy things. So when our process works well, we can achieve things like that. So here you have a copper bracket that was built using the cold gas dynamics pre-additive manufacturing process. This is another example of another copper part that was built by this process following many impacts of particles that do bond together. Here you have a combustion chamber, a special combustion chamber made out of titanium that was built also using the process I'm going to talk about. So that's how I relate this with the spacecraft part of the introduction. So before talking about this process, just a little reminder, geography, for those of you who are not aware. Ottawa is the capital of Canada. It's not very far from Toledo. It's actually less than 600 miles. So we can do an Ottawa-Toledo ride. I would say about 12 hours can be done. So we're not that far from each other. The University of Ottawa is close to downtown Ottawa. It's between what we call here the Rideau River and the Rideau Canal that was man-made. So you get this tiny point here of land, piece of land, and what's in red here is the part that's occupied by the University of Ottawa. And we now have a little part of a campus downtown, and we're expanding also on the other side of the highway with more spaces for teaching and research. So just to give you an idea, the University of Ottawa was founded in 1848. It includes programs in medicine, law, and business. So we call this a comprehensive university in Canada, where you have the major faculties, including science and engineering. It's ranked among Canada's top 10 research university. Well, we're supposed to brag about this, but I'd rather say that, in Canada, we don't have a two-tier system type of university as opposed to other locations. It's fairly uniform. So if you're ranked number 1, number 5, number 10, number 20, the system is fairly uniform, and you get the same type of quality education. In Ottawa, we have approximately 45,000 students on campus, and we have one of the largest co-op program in the country. Now, for the Faculty of Engineering, this is what's called the kernel by building. That's where Dr. Choueiri got most of his education, and his research lab was in the sub-basement here, so it's next to the Rideau Canal. The Rideau Canal gets to freeze during the evening, the winter, and we get to skate on it, which is the longest skateway in the world. We have another building called the site building, where it's mostly for electrical and computer science people, and a new building called the Science, Technology, and Engineering building, where our labs are now located in the basement here. So the former lab that Dr. Choueiri was in CBY is now located in this basement. Faculty of Engineering, about 6,000 students, 1,600 graduate students. We have 11 undergraduate and 22 graduate programs of studies, 15 research chairs. In our department, in my department, the mechanical engineering department, we have approximately 1,000 undergraduate students and 150 grad students. We have a special program in biomedical mechanical engineering program, which is quite unique in Canada, where we combine medicine and mechanical engineering, but in a very mechanical engineering way, where we focus more on the interaction of the mechanical system rather than focusing too much on fine biology. It's a very popular program. And our main research areas are fluids, materials, biomedical, and mechatronics. My lab, the University of Ottawa Cold Spray Lab, started in 1998. We're focusing on the development of green coatings and green coating and additive manufacturing processes. This is my background. Typically, we have 15 group members. So we have postdoc, PhD, master students, some undergrad. Typically, the size of the group, it can vary, but it's around 15. We have 4 different spray systems with all the material characterization tools, so the access, so SEM, TEM, XRD, tensile testing, corrosion testing, anything you name it. We have access to most of these pieces of equipment when we want to test the materials or the parts we're producing. Typically, we work in collaboration with aerospace companies. Some of them I've illustrated here that you might be familiar with. We also work with the national defense on specific reactive coatings. And we work also with non-aerospace companies. One example is Intel. So I would say we get 60 to 70% of all our projects are in direct link with the industry. So cold gas dynamic spraying, let's talk about this. So what is it? Well, let's start with this little movie here. This here is a spherical aluminum particle, which is about 12 micron. So 12 micron, it's thinner than a strand of hair. And here you have what we call the substrate. So it's an aluminum plate. And if we throw this tiny aluminum particle on this plate, this is what you get. You can see that it deforms and it bounces off. So if we look a bit more carefully at what we get on the substrate after deformation, so if we look at this surface on the microscope, this is what you're going to get. You get a crater there. Now, if we throw this ball, this little particle a bit faster, you see that it deforms and it stays there, it sticks. So we get this here. Where the particle, the bottom deforms to such extent that you all actually get jetting here, jetting of material. So our tiny particle deforms plastically and then stick to the substrate. So this is basically the fundamental of the gas dynamic spray process. And if you're doing this many times, so if you have many of those tiny micron-sized particles that you project against a flat surface, they will all deform plastically and stick together and accumulate to form a coating, which might be of various thickness depending on the parameters and for how long you spray. And here I have illustrated a real coating that I'm just turning around. So you have the flat plate, the original flat plate here that you wanted to coat with a special material. And this is your coating here, about 150 micron, 200 micron in this case. And you can see that the coating is made of two different materials here. In this case, it's, I think, alumina and aluminum. So this is the process and how it works. And you're going to put these tiny layers to protect the base material against corrosion, erosion, wear, high temperature oxidation, fretting, and different things like that. So that's how the process does the work. You throw small particles, just like Play-Doh balls on the wall, they deform plastically, stick, and accumulate. Now, how do we do that in reality? We're not throwing the particles one by hand. We're using this setup right here, which is a cold spray gun. So you can see here what you have is a converging, diverging nozzle in this part. So this is pretty much what a rocket engine is. It's a converging, diverging nozzle. So as you know, if you inject a gas, in our case, it's mostly nitrogen, we're going to introduce nitrogen in this setup. The gas will accelerate through the converging, diverging nozzle because you convert thermal energy into kinetic energy and you get a supersonic flow in this zone here at high speed, which reaches about 2,000, 3,000 meters per second, depending on the spray parameter you're using. Whoops, sorry, let me go back. If you want to accelerate the gas to a much faster velocity, what you can do is you can preheat the gas prior to injecting it here. In cold spray, we can preheat it up to 1,000 Celsius. This increases the energy content of the gas and it's going to become warmer and it's going to expand to a higher velocity. Then we inject here our tiny powders, the tiny micron-sized powder. They're injected in this converging, diverging nozzle. They're accelerated to a high speed sufficient to not bounce off, but rather stick. And then if you move the gun or the part that you're trying to coat, you're going to create what we've seen before. You're going to create a coating. So this is how we do it in the lab. This is how the cold gas dynamic spray process does work. So you inject a material that has a little bit of ductility, mostly metals, and then you can get coatings out of them. So the advantages of this process, the main one, it's a low temperature process. Even though we can preheat the gas up to 1,000 Celsius, it expands in the nozzle, so it quickly drops below room temperature. So that means our tiny solid particles do stay in the solid state. So that's quite interesting because it means there's no change in the microstructure or phase because we don't have melting. There's no oxidation because we're using inert gases such as nitrogen or helium. If you start with a powder that has nanograins, well, you don't get grain growth because it's at low temperature. And it's very low thermal input on the part that you want to coat. So that will prevent distortion or thermal distortion. We can produce very dense coating. 100% density is always our objective. Sometimes you have a little bit of porosity. Very high productivity. We can produce coatings and parts with tens of pounds per hour that as a build-up rate. So that is something very distinctive. We can produce very large part and very thick coatings quickly. High deposition efficiency. So when we inject the powder, the vast majority of those particles will deform and stick to the substrate. Very few of them will bounce back if the process is tailored properly. Because our nozzles are very tiny, we don't need masking when we spray or coat a part. If we can use pretty much, well, a lot of different coating and substrate materials, we can apply a coating on many different materials and many different types of coatings. We get a very high adhesion strength, so your coating sticks very well to the substrate. We can reach up to and above 15,000 psi in terms of adhesion strength. And it's a green process because we're only using nitrogen, and the particles that don't stick, we can recycle them. It was supposed to be the holy grail when we started to work with this process. Well, actually, it's not the holy grail. We have to be honest. There are some major limitations. The first one is the low ductility of the coating or the part that we spray, because you have lots of cold working. So there's almost no ductility in your final product. So you need to perform a heat treatment to restore some ductility if you need the ductility for your application. It can be very challenging to spray work hardening alloys or ceramics, although we're starting to be successful to spray ceramics, which is surprising because in ceramics, you don't have the ductility to get your deformation required to stick. But there's different mechanisms that we're finding allow us to spray ceramics. And it's challenging to spray on ceramics because they tend to be brittle, so they tend to crack and explode. So we're still working on these things. Those are very, very difficult challenge to solve. And it's a line of sight process. So it means, right, you're scanning, so you can only spray what you can see. You cannot spray behind things. You can only build up on top of things. So that's also a major limitation. And spatial resolution is also limited. I mean, the size of the nozzle can only be, you can shrink the nozzle size, but up to a limit. So the resolution is probably 25 to 30 microns at best. So that's also a major limitation. So what the hell did I do over the last 25 years? Because it's simple. You take a particle, you throw it fast enough, it deforms and it sticks. That's the process, deceptively simple. So when I started to look at this 25 years ago, it was really cool and interesting for me as a young professor. But people were telling me, well, you're not going to make a career out of this. Well, actually, I did, because there's many questions that we had to answer, and there's still many to be answered. One of them was, okay, how fast do we need to throw the particles to make sure that they don't bounce off and that they stick? So what are the adhesion mechanism in this process? What are the deformation mechanism? How do we know that it's going to deform well? How does it deform? What's behind this? And the spray parameters that you're using on your spray gun, how do they affect the dynamics, the momentum transfer, the heat transfer to the particles and to the part? How does it work? So those are some of the questions that I've tried to answer over the last 25 years, and I'm going to show a little bit of these things during this presentation. So the first one, the adhesion mechanism. Well, there are two adhesion mechanisms. The first one is what we call the mechanical anchoring. So if you have here at the bottom, the top of the part that you want to coat, you can grid blast it hard enough so that you create this intricate topology. So when your particles that you project hit the surface here, they're going to deform, and they're going to basically do just like a Velcro effect and become attached to this intricate topology. So here I have a model, a physical model. So what we've done is we've scanned this and we've imported this and meshed this to try to be able to predict the adhesion strength. So at the bottom, you have the steel substrate that's modeled, and at the top, you have the copper coating that's modeled there based on the cross-section of a real coating we've obtained, and we've tested this for adhesion, and then we wanted to see if we can predict this using FEM. And it allows you to see when we pull on this, look at these area here and here and here, you can see that you have kind of these parts that will prevent the top part from easily detached. That is mechanical anchoring. It's one of the two mechanisms of the two adhesion mechanism, and it can be very strong. You can reach 12, 15,000 psi in adhesion strength from this mechanism. Another mechanism, which is sometimes the preferred mechanism, is a mechanism that's similar to cold welding. So that's why I have the cold welding analogy. When you do cold welding, you have two plates, and of course, any metallic any metal will have an oxide, a native oxide layer. So you put the two plates on top of each other, and now you start to apply pressure on them. What's going to happen is, of course, you're going to get your shear stress then, and the two metallic plates can deform, but you have limited deformation available for the oxide, so the oxide layer will break. If you keep applying pressure, then it means now you have cracks that are available for the two materials to flow through. So you're going to get here the materials that will fill the gap, and eventually you're going to get the two materials that are fresh, oxide free. And if you apply enough pressure, then chemically or metallurgically, you're going to get a bonding. They're going to share electrons, and you're getting just like a regular type of metal where you have metallurgical bonding. So in cold spray, we get that too. We get our particle that we accelerate and the substrate. Both of them have a native oxide layer. So that's why we need to throw this tiny ball fast enough so that you're going to have enough deformation at the interface to break this oxide so that you get this extrusion of material here where you're going to get this intimate contact and then the bonding. So that's metallurgical bonding, and that's why we need to throw the particles fast enough. Otherwise, you don't break the oxide and you cannot get a metal on metal clean surface. So that's the metallurgical bonding mechanism that you get in cold spray. Here you get a cross section of one particle on a substrate, and you can see here there's a physical link at these locations. So you have a gap here for sure, but here you can see a tiny link. So you have metallurgical bonding here at these locations. So it means this particle was not accelerated fast enough to get full metallurgical bonding, but you start to get metallurgical bonding between the particle and the substrate. That's another example where it might be more obvious. You can see the entire initial particle was spherical. The substrate is here, and you can see here a nice metallurgical bonding occurring there. So that's how you get the particles to stick, deform and stick, and you pile them on top of each other, getting cohesion between particles with bonding like this one. If I summarize a little bit here, don't worry, this is very crowded, but let's just focus on the blue line here. So on this axis is the particle velocity at which it impacts the substrate. Here is the percentage of particles that will stick at this velocity. So if you throw the particles at low velocity, they don't really stick. Then at one point, some of them will stick, maybe because some of them have a thinner oxide layer and you can really break it. And you can clearly see a big ramp up at one specific velocity where most of them will adhere. This is what we call in cold spray the critical velocity. That's where the velocity is fast enough that most particles are able to break the oxide layer upon impact, break the oxide layer of the substrate upon impact, and will start to stick. And this deposition efficiency, when you go faster and faster, you get more and more in terms of percentage that will stick to the substrate. However, things are never that easy. You can throw them too fast. If you keep accelerating the particles and throw them faster, now what you're going to do is you're going to start to erode the particle that was there before, or the bouncing energy is high enough that your particle will actually delaminate here. So that's why you have basically a certain window of deposition where you get enough particle that will stick, not too much that will debond to get or build a coating right there. So you have a minimum velocity that you need, but you shouldn't go too fast because you're going to start to erode, just like grid blasting, basically. For each particle, for each material, you have different critical velocities. So here you have kind of a mapping for different materials. So let's say you go with gold. If you want to throw gold particles, you need to throw them at 250 meters per second to start to stick. And if you throw them faster than 600, they're going to start grid blasting. So you have this for a bunch of materials that we've sprayed. The toughest one is the TI-64, where you need to throw the particles at least at 750 meters per second, but not higher than 2250 meters per second, because you're going to start to basically grid blast. So for every material you want to spray, you need to find this deposition window, and you need to tailor your process to make sure that you're in that sweet spot where you get a coating fast enough to get the coating, slow enough that you don't grit blast. So that's an overview of adhesion mechanism in cold spray. Let me switch to my second part right here. Sorry about that. So let's look at the deformation mechanism. How does this work? What happens to a particle when it impacts your substrate? Well, you know that your flow stress is depending on the strain rate, and the temperature. So you've seen this in your material courses where you have the work hardening term, you have the strain rate term, and the thermal softening term. So if we look at the stress strain curve, let's look at the red one here. Well, you know that you're going to get the work hardening. So as you deform, it becomes more and more difficult. You need to push or pull more and more to deform even more. And if you want to have the same material and deform it quicker at a higher strain rate, well, you're going to need to pull harder because of some irreversibilities. So it's harder to deform at the same level or at the same strain at a high strain rate. If you want to bend something slowly, it's easy. If you want to bend it fast, you need to work a bit harder. If you remember for your materials courses, the area under this curve is the work. Most of this work is lost as heat transfer. A little part of it, about 10%, is really going into modifying the microstructure, getting dislocation, movement, and all that to get your deformation. So when you have a high strain rate like that, you're producing even more heat, right? Just like you've probably done this experiment where you take a coat hanger, and a metallic coat hanger, and you bend it back and forth, and you can feel that it's hot because all the work you put in, most of it doesn't go to change the crystal structure. It's lost in heat. So in cold spray, we have a strain rate which is the order of 10 to the 9. So our curves in cold spray are even higher than that. So there's lots of energy that will be transferred into heat in our tiny particles as opposed to deformation or change in microstructure. So when we look at one particle, what happens is when it impacts the substrate, it's going to start to deform, but we deform it so quickly that locally all this energy, most of it is transferred into heat, and you're going to heat very, very locally the material, and now it's going to start to behave like a liquid. So you're going to get what we call the adiabatic shear instability. At the bottom of the particle, that first layer is deformed so quickly that you're going to get lots of heat generated, and the material is going to warm up, and then you're going to get a abrupt reduction in your flow stress, and that tiny layer will start to flow almost like a liquid. So if you throw your particle slowly, you're going to get that, but if you throw it fast enough, you're going to get into this zone where you have lots of energy that's converted into heat very, very locally. We're talking about a few microns, a few nanometers, and that's why you get this sheath here that we call the jetting part. This material was locally at high temperature, not melting temperature, but high enough that basically your flow stress drops and it starts to flow like almost like a liquid. So that's how the particles are deforming. So if we look again at this diagram, this tiny layer here at the interface, that's where all the impact energy is trapped. Some of it to induce dislocation and perform deformation, but most of it in terms of heat. And that's why this tiny layer here now is almost viscous like a fluid. So that's how it deforms. How did we come up with that explanation? Well, it's so fast, we can't look at it directly. So we need to model it to be able to understand what's going on. So we have different length scale for the modeling and different time scale to observe what's going on. What we've done in our lab is mostly looking at a particle impact using continuum theories, allowing us to use FEM modeling. But we went down all the way down to molecular dynamics also to try to understand what's going on. Both of them have some advantages. Both of them have some drawbacks. An example of FEM modeling here. So you have copper particles. Using a model like that, we can understand how they deform, and that's how we could figure out by looking closely that, oh, you get this adiabatic shear instability at one location, and that's why it starts to spread. However, the models, when you use FEM, it gives you an overall idea of what's going on, but you don't get any details of what's going on in terms of the microstructure and all that. So that's why we went to molecular dynamics. Molecular dynamics, the problem is we cannot model a 10, 20 micron particle. We need to have very, very tiny particles, but still it allows us to figure out what's going on. So you can see here, based on molecular dynamics, so that means we model atoms by atoms and we follow them as we deform them. You can see that based on the molecular dynamics model, what you have in gray are atoms that are not following the crystal structure initially found in the material. They're now not behaving as a crystalline structure. So that's what happens there. It's so intense that you lose that crystallinity. You get lots of dislocation, movement, creation, generation. And then you get those zones that now can flow very well. And some of them, as you can see here in the model, can bond with the substrate, and you can see that you have a good mixing of atoms. Eventually, after that, you're going to get recrystallization because this is only after a few picoseconds. It's a fast process. So in the end, they go back into their crystal structure with a refined microstructure at this very, very tiny zone. But these models allow us to figure out what's going on. What we've looked at also is starting with the powder. So here you have the XRD of a Coney-Crawley powder here, and we spray this and we do the XRD of the coating. We see the beta phase in the powder disappears. It's not there anymore, and you get peak broadening. So when we look at this through TEM with the SAED pattern, so that's the SAED pattern of the powder, crystalline powder, nothing special, but that's the SAED pattern of the coating, and you can see that now you have the full ring. So at this tiny interface, we get nanocrystalline structure. So I was lying a little bit at the beginning when I was saying that you don't get any chemical structure change. You do, but at a very, very tiny layer, a few nanometers thick, where you're going to get this nanocrystallization. So again, by studying this, we can better understand what's going on in this complex deformation mechanism. The effect of the spray parameters now, here you can see the velocity as a function of the distance inside the nozzle. So when you go in the nozzle, the gas accelerates to supersonic speed, and these are particles that you would inject depending on their size. So you can see obviously smaller particles will accelerate and get closer to the gas velocity. So that would tell you, okay, try to use small particles because they're going to accelerate a bit more, a bit faster. Effect of the propellant gas nature, gas temperature, gas pressure. Here you have curves of the particle velocity, function of the gas temperature that you use for one specific gun. You can see here when you're using nitrogen at 4 megapascal, that's the pressure and temperature before the gun. As the temperature increases, the particle velocity increases also because you get more thermal energy converted into more kinetic energy transferred to the particles. The effect of the gas stagnation pressure, well, not that much. So it's not really worth it to use super high pressure because changing the pressure in your system, if you know a little bit about gas dynamics and rocket engine, the pressure doesn't change the velocity. The pressure will change the gas density and maybe a better momentum transfer, but it doesn't change the gas velocity. So it's not worth it to increase too much the gas pressure. If you switch to helium, oh, that's great because now helium is a lighter gas, has a much higher speed of sound, and you can see that the particle will accelerate much faster. However, Helium is very expensive and it's a non-renewable resource compared to nitrogen. So despite the fact that we get better performance using helium, we tend to stay away from helium because it's too expensive and not a renewable type of resource. So we spray using nitrogen or air. If you look here at the same effect, if you look at the gas temperature on the tensile properties, as you increase the gas temperature, the velocity of the particle increases and they're going to bond much better. Same thing with the deposition efficiency. At one point now you go fast enough that most of them will stick. Temperature is important. The particle temperature is important because you know, right, the yield strength as a function of temperature, you know that the yield strength can drop quite drastically as a function of temperature. So if we want to spray materials, we'd like to get the particles as warm as possible just before the impact, but it's kind of difficult because in the cold spray process, the temperature in the gun drops very drastically. So it's a bit hard to achieve, but nevertheless, here it tells us a different story, right? You see the small particles, they go very fast, but they cool down much faster than the others because the gas here, if you look at the gas temperature drops because you convert thermal energy into kinetic energy. So the small particles, they drop in temperature very, very quickly. So they go fast, but they're cold. So actually the optimum is not to spray small particles because they go fast, but they're cold. So they don't deform that well. It's better to have larger particles that go a bit slower, but that are a bit warmer. Another parameter is the standoff distance. So the standoff distance is the distance between the nozzle and the part that you want to coat. Because the flow is supersonic, you're going to get a shock wave here, which will be detrimental. So if we look at the deposition, if we look at the deposition efficiency, if you're very close to the nozzle exit, the particle velocity is not very high, the deposition efficiency is not very high. If you move a bit further away your nozzle, now your particles will have more time to accelerate. The shock wave here will not be as strong, and you're going to be able to get a better deposition efficiency. You have a sweet spot where you almost get rid of that bow shock wave at the substrate and the particles get a very high velocity. If you move way too far from the surface you want to coat, now the jet velocity drops and the particle velocity drops, and then you're going to start to see a decrease in the deposition efficiency. Spray angle, so you can spray at 90 degrees or change the angle. Well, if you change the angle, of course, the normal velocity compared to the substrate drops, and you're going to get a decrease in deposition efficiency and an increase in the porosity because they won't deform as well. Same thing in the tensile properties of the coating or the parts you're producing using that. As you increase the spray angle, the properties will go down. The gun speed, as you increase the gun speed, so that's a coating of 4.25 millimeter. When you spray at 5 millimeters per second, that's your gun speed. If you increase the gun speed, of course, your coating decreases in thickness, but look, it doesn't decrease linearly. See, we've doubled the velocity, but it's not half of the thickness. Why? Well, here's what you have. This is the thickness as a function of the speed and the deposition efficiency as a function of the speed. The higher the speed, the more efficient that you are. And the reason is if you go too slow, you're starting to build a pyramid. So that means that you're going to start to have particles that will hit a surface that's not 90 degrees. So that's why we try to go with very, very high scanning speed so that we build uniformly to get the better efficiency. Overlap size, of course, our coatings, they always have this little bump there. So depending on the way we spray, we try to make sure that we have an overlap to minimize the bump and the overall surface look like the red curve here, which could be a few microns or less than that. We also have worked on the development of a enhanced system where we're using laser assisted cold spray. So we have a laser on the side that will shine directly where the particles will impact. And the reason is to preheat the substrate just before the particles hit the substrate to make sure that it's a bit more ductile. So you have an example here of the system. When you spray, this is a large cylinder, and we spray copper traces on top of it. So you have the laser here, and it shines just there to locally preheat just before we spray to enhance the ductility. So that's one way also to promote adhesion and promote deformation. Okay, so time is flying, so I'm going to try to accelerate a bit and show just a few applications. One of them is the repair of Alclad aircraft skin that was done in collaboration with Boeing. So the aircraft skins are usually made out of Alclad, so that's an aluminum alloy, and on top of it you have pure aluminum to protect against corrosion. And sometimes you get these surfaces damaged, and the way to repair it for them was to take out the panel, strip the full panel out of its aluminum, and then reclad it, which is very time consuming and very expensive. So by using cold spray, we can have a portable cold spray system where we go and we spray directly. So we just grind a bit out where the damage is, and we spray right there the pure aluminum coating, and we polish it, and there you go. So here you can see that's the original surface, and that's the cold spray coating compared to using other thermal spray processes. You can see it's a pure aluminum coating as opposed to an aluminum coating with tons of crap in it. So the cold spray process, we've developed the parameters and application and demonstration that it can be used to repair aircraft skins, and that's actually now a Boeing internal specification that they use to repair aircraft skins. So you can see here one example where we did a damage here, and then we spray, and then we polish, and then you have the repair there. That looks great. You can't even see where the repair was. So I'll just try to fly a little bit to demonstrate that we went to adhesion strength that were beyond what they were hoping for, expecting. And 3-point bending was to demonstrate that it doesn't delaminate. So it does crack, yes, but it doesn't delaminate, which is exactly what happens also when you have the pure Alclad thing there. And corrosion, we went under 5,000 hours of accelerated corrosion testing, and yes, it behaves as it's supposed to, so that's why they've adopted this. Another application that we use is for gas turbine bond coat. So when you have a turbine blade in a gas turbine engine, you have the base material, and you're going to cool it, and you want to protect it against the hot gases coming from the combustion chamber. So what you do is you apply a ceramic coating right there. The problem with the ceramic coating that you apply on your base material is they don't match in thermal expansion coefficient. So it's going to delaminate. So what we do is we apply an intermediate coating called a bond coat, which does have a thermal expansion coefficient in the middle between the base material and the ceramic top coat that you're applying as an insulator. And on top of it, the ceramic layer, it lets oxygen go through. So the oxygen can go through and attack your base material. So this bond coat also serves as a barrier to prevent oxygen to go attack your base material by forming a tiny layer called a TGO, thermally grown oxide layer, an alumina layer that grows out of your bond coat that prevents the oxygen diffusion. So that's what we're producing in the lab. We're specializing in producing special bond coats. So here we started with a co-nichrality powder. This is what it looks like. You have your beta phase there and your tantalum rich phase and the matrix. This is the turbine blade that we spray on. This is the microstructure of the single crystal blade. And the idea here is actually to go a bit counterintuitive. What we've done is we've sprayed the coating using very, very poor spray parameters. The reason for that is we want to have a low deposition efficiency, to have only a few particles once in a while that stick, and lots of them bombarding them on top of it. By doing that, you're going to get so much bombardment that you're going to get a nanocrystalline coating produced in situ. So you start with regular cheap powder and it becomes nanocrystalline. And being nanocrystalline will enhance the properties, the properties that we're looking for to protect the turbine blade. So here you have an idea of the coating. It's very thin, 20 microns is good enough. You see the particles are well deformed and we've bombarded them a lot. And when we go to the TEM, we can see that we get a nanocrystalline structure there, which will enhance the high temperature oxidation properties of this coating. Quickly, before I end, another application is used nuclear fuel storage. This is in partnership with Nuclear Waste Management Organization. So in Canada, what we're going to do with our nuclear waste, we're going to get the used fuel bundle. Just like everybody else, we put them in a steel container, and then we apply a copper coating on top of the steel container, and we dig a hole 1 kilometer down or half a kilometer down in the Canadian Shield, and we're going to store them there in bentonite. And we need to have a copper coating because copper has been shown to be very, very stable when you put it in the bentonite clay. So what we do is we take the fuel bundles, put them in this container, and then we need to cap the container. So we screw the container and we weld it. The weld needs also to be protected by copper, so that's what we do using cold spray. So you see the cap here of the container and the weld here, and after that, we do cold spray this with copper and we polish it before it gets put underground. So the video you saw a bit earlier was when we were trying out all the spray parameters to be able to coat the weld region. Cold spray additive manufacturing. So additive manufacturing has been a hot topic for a while, and people will tell you cold spray is not an additive manufacturing process per se, and they're right. We use it at every flavor, but it is a process where it's a layer by layer building process, and you can build part out of it. And this is one of the first cold spray additive manufacturing product that we've produced. Those are very tiny pin fins that we were building on a plate, and we were building them on top of each other to have a super compact, high efficiency heat exchanger that we've built for a Formula One race car team for their intercooler. So we did 3D printing using cold spray of the intercooler using this technology to have a very compact, high efficiency heat exchanger. To finish here, one nice example in action of cold spray for 3D printing. Here it's a titanium structure that we're spraying to study the mechanical properties. So it's made out of titanium, titanium alloy. So you can see that it would be basically part of an aircraft structure that instead of machining a huge titanium ingot, which is very expensive, very hard to machine, we start with this titanium alloy powder and we build the part that we want to have and study. So to summarize, cold spray has evolved from a coating technology to a repair technology to an additive manufacturing technology, and there's lots to be done, especially for additive manufacturing, because now you need to start looking at the robot, how to move the part. Sometimes you need to perform laser in situ heat treatment. That's something we were also working on. So there's still lots of things to do, but it's for sure a very intriguing technology that can be used for specific niche application, and that works very well. So with that, thanks a lot for the invitation, and I'm pretty happy to answer any question.
Thank you so much, Dr. Jodoin, for this awesome presentation. The floor is open for questions. You can write it in the chat, or you can let me know so I can unmute you. Okay, I will start by myself. I have a question about the first part of the presentation and about like the relation between the velocity of the particle and the efficiency of the deposition. Is this independent of the substrate? Like
Yes and no. Typically, it's no. The reason is once you've built up that first layer, the material is spraying on itself, right? So no
Yeah.
matter what is underneath, it's the same impact physics. So I would say for the very first layer, it is extremely dependent on what's the substrate. After that, we tend to see that very quickly after 20, 25 micron thick, it's now the same physics no matter what is the substrate.
Thank you. And Dr. Bertrand has a question. I will unmute you. Dr. Bertrand, yeah, okay. Go
Can you
ahead.
hear
Thank
me?
you. Yes.
Okay. Just a quick question. In fusion processes, usually the oxide is actually coming on top of the mouth pool and floats, meaning that the oxide is not going inside the material. But here, what is your experience and what is your thoughts about all the oxides around the powder particles when you shoot them? Is the oxide trapped, and does this make a limitation in the material type that you can use?
So what we've found so far is we have a very, very hard time tracking oxide inside the coatings. So most of the time it means that we spray fast enough that the shearing process basically ejects the oxide from there. Now, it's kind of difficult to prove because it's a very, very pinpoint type of study, right? You're going to look at one specific location, but using the common tools that typically are used, we don't find an increase in the oxide in the coating, and we tend to say that the oxide is expelled by the explosive nature of the impact.
Okay, that's interesting. And I remember I had a discussion with Steve Yu, and he's using that for copper,
Yes.
basically, and copper, basically deposition, or you can call it printing. He mentioned that he had that oxidation issue, and that copper usually, especially if you want to go for high conductivity, from the electrical standpoint, the cold spray doesn't give that properties of
Yeah, so
expect.
you have to be very careful to start with a powder that is not oxidized. So
Hmm.
so it's the toughest part is to make sure that you have a good powder. You cannot improve the quality from what you have initially. So if you have a very high purity powder, you keep it in a glove box or something to minimize the oxidation. What you get is as good as what you started with. Now you have to be careful because if you use too high spray parameters, even though you're not heating a lot, even though you're using nitrogen, you can have contamination, you can have oxygen in your spray chamber, and that can lead to oxidation between the passes, right? So you have to be careful about that. The powder first needs to be very pure, and then you might have to spray at parameters that you're not used to spray because you want to avoid oxidation for a specific application like that. So it's not easy. So people tend to say, oh, for copper, I spray at this pressure, this temperature, it gives me fully dense, well adhered coatings. But if you're looking to minimize or to make sure that you expel the oxide layer, start with a powder that's not too oxidized and maybe change the spray parameter to reach that. So that's something we've discovered. And the problem is you need to be very, very careful with the powder handling to make sure that it doesn't contaminate.
Great. Thank you. Thank you, Bert.
Thanks for the question. I think you're muted.
Yes, thank you. So we have a question in the chat from Hussein Abedi. And the question is, can cold gas spray become a standard manufacturing method and not be limited only for coating or small-sized heat exchangers?
Yes, right now, mostly in Europe, it's used for a large part. One of the main advantage is the throughput you can get. So there are some applications where you get a shaft that's about 10 meter long, and you coat it using that within a few minutes instead of hours or days using other processes. So it is used for a very large part. Right now, there are lots of use in Europe in particular, but because the process it's not a new process, but everybody is still very secretive about what they're using with it because it gives them an edge. So I know some companies because I've worked with them that are using it for specific applications, but they don't want to disclose it because right now it's their edge using that. But yes, it can be done to have you can build almost unlimited size using that, so that's not an issue. And as opposed to let's say a power bed method, you don't need a build plate, right? You can just you can grow outside of a chamber. So yes, you can. It is not limited for coating or small size in the exchanger.
Thank you. And another question from Dr. Ameli in the chat here. I'm just reading what he wrote. A wonderful talk overall. How much fluid mechanics research do you envision in the cold spray field in the future? For example, understanding the particle shock wave substrate interaction among other particle Leiden flow parameters or particle volume fraction.
What I see in the next few years is a real push for more understanding, but not using metals, using ceramics. That's where we need to push even more to understand. So there's lots of modeling to be done to understand how to spray ceramics. So that and right now people are doing it by using vacuum cold spray. So they spray in a vacuum chamber to remove or to diminish the shock wave that you get there, and these things have not been studied well. People do build ceramic coatings, but it's still not well understood. The fluid mechanics part of operating in a partial or a low pressure environment has not been studied well. So I see this to me as the driving force in the next 5 years to understand better that part of the process.
Thank you so much. Any other questions?
Karim, if I may just have a couple quick questions.
Yeah, sure.
I think we're over time, so I guess brevity. So when you were looking at the types of gases used, based on what I was looking at, I'm assuming using argon would make it even worse because it's a heavier gas.
Yes.
Okay. And in
So I'd
terms,
like to use hydrogen actually, but I need to
yeah.
convince my dean.
In terms of the plot that you had for, I guess, the guns, shotgun process, basically looking at those curves on that image, they kind of look to me like it has a logarithmic relationship. So if you plot the y-axis as logarithmic, then you would get two straight lines. Or I'm asking this because if you're trying to think of this not from a numerical perspective, but a theoretical one, it really helps if things vary logarithmically. So is that the case? Would you get two straight
It
lines?
is for the curves I've shown you, it is, but we've designed different nozzles where it's different.
Okay.
So that's something we've done using CFD. We've tried to optimize. You know, sometimes we need to spray a coating in an inside diameter, so we want to reduce the length of the gun, so we need to change the geometry. Sometimes we want to reach faster velocities, but not at the expense of temperature. So we do lots of CFD work to optimize the nozzle configuration based on the application we're looking for.
Okay, wonderful. Well, I'd like to really thank you, Dr. Jodoin. It was a wonderful talk. So I'll
Thanks for the invitation. And yeah, if any of you cross the border, you're not that far from Ottawa, so you're all welcome to visit.
Thank you so much, Dr. Jodoin, for your time and the nice presentation. And yeah, we don't have other questions. So thank you so much. It was nice meeting you, and have a good day.
Thank you all. Have a good weekend.
You too. Thank you.
Take care.
Bye-bye.
Take care.